Everyone. So our topic is all about the spectroscopic methods. My name is Christian Willie Pablo.
And my name is Alden Davis Kagan.
So what is spectroscopic methods? Spectroscopic methods refers to a set of techniques used in analytical chemistry to study the interaction between matter and electromagnetic radiation. This method involves the measurement and analysis of the absorption, the emission or scattering of light or other forms of electromagnetic radiation by a sample.
And also, spectroscopy allows scientists to obtain information about the composition, structure, and properties of substances by analyzing the way they interact with different wavelengths of light. By measuring the intensity and wavelength of light absorbed or emitted by a sample, spectroscopic methods can provide valuable insights into the chemical composition, molecular structure, and concentration of substances.
There are several types of spectroscopic methods, and these include the five methods that includes UV visible spectroscopy,
Infrared spectroscopy,
nuclear magnetic resonance,
and the mass spectrometry.
then the Raman spectroscopy. So
The-
what is UV visible spectroscopy? This method involves the measurement of the absorption of transmission of ultraviolet and visible light by a sample. It is commonly used to analyze the electronic structure and concentration of compounds.
And the second one is the infrared spectroscopy, or the IR. This measures the absorption, transmission, or the reflection of infrared light by a sample. It's used to identify functional groups, analyze molecular structure, and determine the presence of a certain chemical bonds.
Then we also have the nuclear magnetic resonance spectroscope. The NMR involves the measurement of the interaction between atomic nuclei and a magnetic field. It provides information about the chemical environment, molecular structure, and dynamics of molecules.
And also the mass spectrometry. This is a technique that measures the mass to a charge ratio of ions. It is used to determine the molecular weight, elemental compositions, and structural information of compounds.
Then we also have the Raman spectroscopy. Raman spectroscopy measures the scattering of light by a sample. It provides information about molecular vibrations and can be used by chemical identification and analysis.
So here is the classification of spectroscopic methods. It is the nature of radiation measured, and the type of spectroscopy depends on the physical quantity measured. The type of spectroscopy depends on the physical quantity. Then normally, the quantity that is measured is an amount or intensity of something.
Also, electromagnetic spectroscopy involves interactions with electromagnetic radiation or light. Ultraviolet is visible spectroscopy is the best example of the electromagnetic spectroscopy. It also involves the interaction between electron beams. Then the Auger spectroscopy involves inducing the Auger effect with an electron beam.
And also, the mechanical spectroscopy involves interaction with the macroscopic vibrations such as phonons. And an example is acoustic spectroscopy involving sound waves. And the mass spectroscopy involves the interaction of charged species with magnetic or electric field, giving rise to a mass spectrum.
Then it also involves the measurement process, which most spectroscopic methods are differentiated as either atomic or molecular, based on whether or they not apply to atoms or molecules. Along with that distinction, they can be classified in the nature of their interaction. The absorption spectroscopy uses the range of the electromagnetic spectra in which a substance absorbs. Then measurement process, then the atomic absorption spectroscopy and various molecular techniques such as infrared spectroscopy. In that region, a nuclear magnetic resonance spectroscopy in the radio region. Then, the emission spectroscopy uses the range of electromagnetic spectra in which substance radiates or emits. The best example is the luminescence, molecular luminescence techniques include spectrophotometry.
And also the scattering spectroscopy measures the amount of light that a substance scatters at certain wavelengths, incident angles, and polarization angles. Also, the scattering process is much faster than the absorption emission process or the Raman spectroscopy.
The electromagnetic radiation. The EMR or light is a form of energy whose behavior is described by the properties of both waves and particles. The optical properties of electromagnetic radiation, such as diffraction, are explained best by describing light as the wave. Many of the interactions between electromagnetic radiation and matter, such as absorption and emission. However, it is better to describe by treating light as a particle or photon. Wave properties of electromagnetic radiation consist of oscillating electric and magnetic fields that propagate through space along a linear path and with a constant velocity. For example, in a vacuum, electromagnetic radiation travels the speed of light, which is 2.99729 times 108 meters per second. Electromagnetic radiations moves through a medium other than a vacuum with a velocity, which is v, less than that of the speed of light in a vacuum. Oscillations in the electric and magnetic fields are perpendicular to each other and to the direction of the wave's propagation.
So, the wave parameters. The time required for the passage of successive maxima through a fixed point in space is called the period or P at the radiation. The frequency or V is the number of oscillations of the field that occurs per second and equal to 1 or P. Another parameter of interest is the wavelength, which is the linear distance between any two equivalent points on successive maxima or minima of a wave. And also multiplication of the frequency and reciprocal seconds by the wavelength in meters give the velocity propagation. It is important to realize that the frequency is determined by the source and remain invariant regardless of the media traversed by the radiation. In contrast, the velocity of propagation, v, the rate at which the waves front waves through medium, is dependent upon both the medium and the frequency. In a vacuum, the velocity of radiation becomes independent of frequency and is at its maximum. The velocity, given the symbol c, has been accurately determined to be 2.99792 times 1010 cm per second, thus for a vacuum. In any other medium, the rate of propagation is less because of interactions between the electromagnetic field of the radiation and the bound electrons is the atoms of molecules making up the medium. Since the radiant frequency is variant and fixed by the source, the wavelength must decrease as passes from a vacuum to a medium containing matter wave number, which is reciprocal of wavelength.
Spectroscopy based on absorption. It is a technique used to study the interaction of electromagnetic radiation with matter. It involves measuring the absorption of specific wavelengths of light by a sample to determine its chemical composition and physical properties. Absorption in spectroscopy is commonly used in various fields including chemistry, physics, biology, and environmental science. It has application in areas such as pharmaceutical analysis, environmental monitoring, forensic analysis, and material characterization.
So the atomic absorption spectroscopy, or the AES, is a technique used to determine the concentration of specific elements in a sample by measuring the absorption of light by the atoms of those elements. It is commonly used in analytical chemistry to analyze the elemental composition of various substances. Atomic absorption spectroscopy is widely used in various fields, including the environmental analysis, chemical chemistry, food analysis, and the metallurgy, to determine the presence and concentration of elements in samples.
Now let's now move on to emission spectroscopy. It is a technique used to study the emission of electromagnetic radiation by atoms, molecules, or ions. It involves analyzing the wavelengths and intensities of emitted light to gain information about the composition and properties of the emitting species. Emission spectroscopy is widely used in fields such as analytical chemistry, environmental monitoring, astronomy, and material science.
And also the photoluminescence spectroscopy is a technique used to study the emission of light from a material after it has absorbed photons. It involves analyzing the wavelengths and intensities of the emitted light, gain information about the electronic and optical properties of the material. For example, in semiconductor research, photoluminescence spectroscopy can be used to characterize the electronic properties and defects in semiconductor materials. In the field of biophysics, it can be used to study the fluorescence of biomolecules and prove their interaction and dynamics.
Atomic emission spectroscopy. It is a technique used to analyze the emission of light from excited atoms. It involves measuring the wavelengths and intensities of the emitted light to identify and quantify the elements present in a sample. This technique is widely used in various fields such as environmental analysis, metallurgy, and forensic science. It provides valuable information about the elemental composition of samples and can be used to detect trace amounts of elements.
So let's proceed to the spectroscopy based on scattering. It refers to a technique that analyzes the scattering of light by particles or molecules in a sample to gain information about their size, shape, composition, or interactions. So there are two main types of scattering spectroscopy: Rayleigh scattering and Raman scattering. So let's define first the Rayleigh scattering. Rayleigh scattering occurs when light interact with particles or molecules that are much smaller than the wavelength of light. It is responsible for the blue color of the sky during the day. In Rayleigh scattering, the incident light is scattered in all directions, with the scattered lights having the same wavelength as the incident light but different directions. Rayleigh scattering spectroscopy is used to study the composition and properties of particles or molecules in a sample. By analyzing the intensity and wavelength, the distribution of the scattered light, information about the size, concentration, and refractive about the index of scattering particles can be obtained. This technique is commonly used in atmospheric science, aerosol research, and monoparticle characterization. And the last one is
The Raman scattering. Raman scattering occurs when light interacts with a vibrational or rotational modes of molecules in a sample. It involves the inelastic scattering of photons, resulting in a shift of wavelength of the scattered light. The shifted wavelengths, known as the Raman shifts, provide valuable information about the chemical composition and molecular structure of a sample. Raman scattering spectroscopy is used to identify and characterize the chemical bonds, functional groups, and molecular vibrations in a wide range of materials. By analyzing the Raman spectrum, which consists of peaks corresponding to specific vibrational modes, researchers can determine the presence of a certain compound study molecular interactions and investigate phase transitions. Raman spectroscopy finds applications in chemistry, material science, pharmaceutical analysis, and forensic science, among others. So that ends our topic about the spectroscopy. Thank you and God bless everyone.